This episode is brought to you by Brilliant. The solar system is full of wonders we're only beginning to discover and explore, but what will we do in the future when all that stuff is just getting in our way? Humanity mostly lives, works, and plays on only a small fraction of Earth's surface, and virtually all activity here is limited to maybe the first 10 meters of dirt, rock, water, and air on that surface. But the ground goes down nearly 1,000,000 times deeper than that. Similarly, the Earth receives less than 1/1000,000th of the light the Sun puts off, and even when we add in all the other planets, moons, and asteroids in our solar system, it's still only a tiny fraction of the Sun's light that falls on these worlds and mostly goes to waste there. For scale context, as sunlight is essentially the ultimate fuel all life runs on, it is as if we produced enough food for a vast empire, but only had one single person eating. Indeed, it is even worse than that, as Earth, the only place known to host life, is quite wasteful with the light it gets, especially from an anthropocentric perspective. The Sun produces around 4 trillion times the power a human actually runs on. From the center of the Sun, where fusion takes place and makes the power that runs our life, to the final endpoint of running a human, only about 1 watt out of every 50 quadrillion produced actually is running a human, with the rest all being sucked up by middleman processes or outright waste. To give a better perspective, it would be like producing enough food to feed every person, past and present, of which only one single bite from one single meal would be eaten by one single person, with an entire mountain worth of leftovers. This then is the reason why we might consider dismantling our solar system, not with destructive intent, but out of recognition that the default setup doesn't lend itself to being efficient for life. It's essentially the notion that while a cave in a mountain is a very handy and easy place to shelter, that mountain has a lot more living potential contained within its raw resources than is a mountain itself. Using that analogy, terraforming other planets to live on would be like finding a dozen or so other caves that weren't really ideal homes and chiseling them into better ones, giving you a dozen times more living space, while dismantling that mountain to build stone houses, or in this case artificial megastructures in solar orbit, would get you many millions or even billions of times more living space. Of course, space is hardly our bottleneck in our solar system, because we've got a ridiculous amount of empty space. Indeed, even if you scattered every human around the solar system roughly evenly over a sphere that enclosed the solar system out to Pluto, you'd have over 1,000,000 kilometers between you and your nearest neighbor, and a volume to yourself not only bigger than Earth, but bigger than the entire Earth-Moon system. So space is not at a premium in outer space. Rather, it's stuff like raw materials to build with, energy to run on, plus all the biological, mechanical, or electronic problems we tend not to think of normally, like getting rid of waste heat or avoiding gravitational collapse. That's probably a good place to begin on the dismantling concept, because heat and gravity are two very big constraints when it comes to disassembling existing worlds or building new ones. If you're a channel regular, you already know what we mean by building new worlds, but if not, see our megastructure series, where we talk about building things like artificial planets, shell worlds being the main example, or artificial Earth-like habitats, typically the O'Neill cylinder, though we covered a bunch of more grand designs a couple weeks back in our episode Continent-Scale Rotating Space Habitats. And that's essentially what we're looking to build that will require whole planets worth of raw material, not to build a single vast habitat, but to build many of them, so many that they take up and use most or all of the Sun's light, rather than letting it go to waste by radiating off into empty space. This is the notion behind a Dyson swarm, often called a Dyson sphere, a cloud of constructs, be they space habitats or solar panels or whatever else we desire, that engulfs a star to use up most of its energy. This is generally assumed to be the end state of any solar system that technologically advanced life dwells in long enough. We call these Kardashev 2 or K2 civilizations, one using all the energy of a solar system, with K1 using all the energy of a planet, or K3 utilizing the entire energy production of a galaxy. At its beginning, a solar system is a big cloud of gas, mostly hydrogen and helium, but with lesser amounts of other materials, where we see some clumps begin forming. As those small clumps form, they develop enough gravity to pull in more material. Eventually, one or more of these clumps will gain so much mass that it can ignite as a star, Other clumps either get swallowed by it, clump together to form smaller stars or planets around it, and thus you get a solar system. When we think about a star, we think of all that fusion going on and think that's where all the heat comes from, but in truth a big part of it comes from gravity while it formed, and you have to pay in all that energy to pull that matter back away from that planet or star. We call this energy the gravitational binding energy, and it's what makes freshly formed planets hot, as every particle coming in to join that world picks up speed as it falls in, and that turns into heat as it starts colliding with other material and slowing down. Doubling the mass of an object does a lot more than double its gravitational binding energy though. Most objects aren't uniform in density, as the heavier elements tend to sink to the center, but as a simple approximation, a sphere of uniform density will have its gravitational binding energy rise with the square of mass and fall off with its radius. However, mass generally rises with the cube of radius, so that a planet twice the radius or width would generally have 2 cubed or 8 times more mass. So a twice as wide planet would have mass squared or 8 squared or 64 times more gravitational energy, divided by 2 for having twice the radius, or 32 times more energy for only having 8 times the mass, meaning it has 4 times more energy per unit of mass. As a result of this, a planet with 1,000 times the mass of another but the same density would be expected to be 10 times wider, but have 100,000 times more gravitational binding energy, and 100 times as much energy would be needed to lift away a single unit of mass off that world as from its much less massive counterparts. This is a large part of what makes the asteroid belt and smaller moons so attractive as sources of raw material. Not only do they lack any atmosphere your mining spaceship would need to plow through to get off them, or your mass drivers need to shoot through to extract material from them, but it simply takes way less energy to fight off the gravity or pay that gravitational bill. We do not have a completely accurate picture of Earth's density in terms of its layers, so calculations of Earth's gravitational binding energy vary a bit from model to model, but are generally around 2 times 10 to the 32nd joules of energy. That's a lot of energy, something like 1 trillion times the annual energy consumption of humanity, and 500,000 times what the sun's total output in a given second is. So when you see a planet getting blown up in science fiction, most memorably by the Death Star in Star Wars, keep in mind for them to blow a planet to smithereens in one quick blast a second long, means whatever power source was for that weapon, it was 500,000 times more powerful than our sun, and that a Dyson swarm built specifically for turning our sun into a big laser beam weapon, what we call a Nyko-Dyson beam, would need to focus all its energy on an Earth-sized planet for around a week to evaporate or explode it. That's a thing to keep in mind for your extraction processes too. Unless you are vaporizing a planet this way, all that heat produced by your lifting engines, be they spaceships or mass drivers, also has to radiate away so it doesn't melt your equipment surface side, or your citizens if they are still there. As Earth only gets about a 2 billionth of the sun's light to maintain its current temperature, you need about 2 billion weeks to radiate that much heat away as you disassemble the planet without it raising the temperature significantly or requiring special cooling efforts, like those we discussed in Matryoshka shell worlds, or around 40 million years. You could go much faster, but there's always going to be waste heat in the extraction process you need to deal with if you are not vaporizing the planet outright. Alternatively, to take apart Jupiter, 300 times the mass of Earth, though also less dense and proportionally wider, would take about 10,000 times as much energy, 200 years worth of solar output, and cost about 30 times as much energy per kilogram removed as it does on Earth. Keep in mind that we spend thousands of dollars to get a kilogram off Earth right now, too. On the flip side, the Moon, still in the top 20 most massive objects in the solar system, which contains millions of large rocks, is almost the reverse of Jupiter at a little less than a 20th the energy cost per kilogram off Earth, and something like 700 times cheaper than Jupiter per kilogram. In the most extreme cases, the Sun's own gravitational binding energy is around 1 billion times that of Earth, and would take about a 500th of all the energy the Sun will produce in its existence to pull it apart. Things like white dwarf stars and neutron stars are far worse, while black holes are impossible to dismantle. While a modest asteroid about 6 or 7 kilometers in radius, containing maybe 1 billionth the mass of Earth, would only take about 1 millionth of a billionth the energy to disassemble as Earth would, and cost a mere millionth as much energy as on Earth to take a kilogram of mass from. Needless to say, this is why mining asteroids for raw material for space habitat construction, not just precious metals, is so appealing. Unfortunately, the mass of the entire asteroid belt is less than 1,000th of what the Earth's is, and most of that mass is tied up in Ceres and a dozen other major asteroids, while the other million or so asteroids of noteworthy size share only the remainder between them. You start with the low-hanging fruit as you build up your solar system, mining these less massive and much cheaper to dismantle places, and moving up as you run out, potentially all the way up to the sun itself using a method called star lifting that we'll discuss in a bit. Two caveats though. First, we shouldn't assume raw energy is the same as actual cost. Even limited to just dismantling a planet, your energy bill isn't likely to be your only or even necessarily your principal cost, even if you're using robots not paying salaries. Then you've got all the transport and construction considerations to factor in. There's also the availability of energy too. Star lifting mass right off the sun may be the most energy intensive place to do it from, but you also have a massive power supply right on hand to fuel that. As an example, it does take more energy to build a rocket and launch it carrying a payload to Earth's orbit than it does to smelt that payload if it were raw ore. When you get down to even large moons though, that's no longer the case, and the general smelting, refining, and manufacturing energy budget is going to be much larger than the dismantling energy involved. Even Ceres, the biggest and most expensive asteroid to mine off of, only has an escape velocity of half a kilometer per second, which will be a kinetic energy of 125,000 joules per kilogram. That is 500 times less than the kinetic energy of Earth's escape velocity, but more relatably, that's about how much energy your microwave puts into food if you have it running for about 2 minutes. The same amount of time and energy as my own microwave just spent reheating my coffee, which I let go cold and untouched while distracted working on this script. Obviously, that is way less energy than you need to smelt some bit of metal ore into something useful. It's also worth keeping in mind that dismantling the entire solar system, minus the sun, would only take the sun's energy output for a couple centuries, and virtually all of that would be spent on Jupiter, which makes up about half of the non-solar mass in our solar system, but nearly all of the binding energy. Indeed, if we ignore the gas giants, we'd only need about a month of solar output for dismantling every last rocky planet, moon, asteroid, and comet orbiting our sun. Considering the scale of such an endeavor on the construction side, we are after all not dismantling the solar system for idle entertainment, but rather raw materials for building stuff, a couple centuries isn't much, or even 10 times that long if you're not being super efficient or rushed, and you are not using any significant part of that total solar energy till you start building tons of megastructures out of these raw materials. As for our second caveat, and on the topic of megastructures, the asteroid belt seems tiny when compared to Earth, which is nearly 3,000 times more massive. However, we only inhabit a tiny thin layer of Earth's crust, and if you went 1/3000th of the way to Earth's center, you'd already be around as deep as our deepest mines tend to go. If you ground up the whole asteroid belt and laid it down as a thin sheet about 10 meters deep, that sheet would be about 100 billion square kilometers, a square 310,000 kilometers or 200,000 miles a side, and containing 200 times the surface area of Earth, land and sea combined. That's maybe a little thin on the ground, and we'd still need 10 million times the mass to fully use the sun's light, but it's nothing to sneeze at and certainly seems a far more productive use of those asteroids than mining them for precious metals, which you could do anyway, let alone letting them sit there mindlessly and fruitlessly banging into each other in the asteroid belt. Earth, on the other hand, being about 3,000 times more massive, could be dismantled and built into the equivalent of 60,000 times as much habitable land as Earth's surface, though that would only take us up to a few hundred thousandths of the area the sun could comfortably light. Still, it is 60,000 times the room we have now, and you could stretch that out quite a lot thinner if you needed to. This is the core concept though, fundamentally the same as our mountain cave analogy at the beginning. We can be content with our one cave here on Earth, or we can put a lot of effort into making a handful of other caves reasonably comfortable too, by terraforming those other planets. Or we can dismantle that mountain and make 1 billion artificial caves with much nicer and roomier interiors, in the form of stone houses. We dismantle our solar system to build something far grander and far friendlier to life. I often get asked by folks if we actually have enough mass in our solar system to build a Dyson sphere or swarm, and the answer is yes, but. It depends a lot on what you're making that swarm out of, and critically we always call it a swarm because that is what the late great Freeman Dyson had in mind when he discussed the concept of a Dyson sphere originally. not its common portrayal as a big hollow inverted planet around a star. A Dyson swarm isn't really a megastructure in and of itself, any more than a city or a nation is. Rather, it's a collection of tons of different structures, which can be standard and uniform, but would probably vary wildly in size, design, and purpose. It would also likely change with time. As an example, your Phase 1 Dyson swarm is probably going to be mostly composed of big solar collectors, and them mostly thin metal foil mirrors reflecting and concentrating light. A classic Dyson sphere, that big metal shell with just 10 meter deep soil, would take more than the entire mass of Jupiter to build, and of course Jupiter is mostly hydrogen and helium, not rock. And while its core contains a good deal more metal than Earth does, it wouldn't be enough to do a full solar englobement, at least of that type. Alternatively, tiny little Mercury, a mere 20th of Earth's mass, is actually more than capable of englobing our Sun, just much more thinly. If we're talking about mostly mirrors and floating in space, the near density of a single kilogram per square meter would be lavishly abundant. Mercury is a lot closer to the Sun, which makes it hotter but makes a sphere of that radius around the Sun much smaller than one out at Earth's orbital distance, about a tenth the total surface area, and thus construction material. Also, such heat isn't a big consideration for swarm objects that are basically big sheets of shiny aluminum foil bouncing sunlight around. Such a swarm of solar collectors would be many thousands of times less massive than their rotating habitat equivalents, in terms of surface area, even if we're assuming fairly thick reflective sheets in contrast to rather thin habitat interiors and hull. You could probably build a good and complete solar collector sphere around our Sun using only the mass of a single decent-sized metallic asteroid. Or a carbon-heavy asteroid for that matter, as the carbon allotrope of graphene might be far more useful for much of these building projects. See the episode The Impact of Graphene. You could also do this around any other star. Brighter and bigger ones would need more mass, smaller and dimmer ones less so, but as a rule of thumb, the needed material would be proportional to the brightness. A Dyson around a star a tenth as bright needs a tenth as much construction material. One 10 times as bright would need 10 times the material, and stars range from tiny red dwarfs giving off only about a 10,000th the light of our Sun, to behemoths giving off 1,000,000 times as much. Key notion though being that any solar system should have enough raw material for this most basic of Dysons, the solar collector, and you could use the excess material for habitats or other constructs of a more compact nature than a thin solar collector foil. Also again, these are not actually solid spheres, they are just a cloud of orbiting objects, so there's no downside to building a partial one or building in steps incrementally. If for some reason you only have enough material for space habitats using a mere thousandth of the available sunlight for people, farms, forests, and so forth, that's still many thousands of times the living area of what you'd find available in any natural solar system's collection of terraformable planets. I would imagine that even extragalactic stars ejected from their native galaxies that left most of their planets behind while being ejected would still tend to have enough objects around them to get a partial solar collector going. And partial is enough, because the biggest source of heavy metals in our solar system, or any other, is actually inside that star, and they can be removed. It's rather energy intensive, but so long as you've got enough raw material to build the apparatus, you can lift materials off a star, which of course provides the power you need for the process. Essentially, we use magnetics and mirrors to enhance solar wind output and capture what blows off. We call this star lifting and have detailed the various methods and how they work in our episode on that topic, but in a nutshell, your typical star is mostly hydrogen and helium, but is around 1% of other materials or metals. Metals in astronomical terms means anything that isn't hydrogen or helium, so includes stuff like carbon and oxygen, not just iron, and the metallicity of stars varies a lot, but our own has a metallicity of about 1.2% of its mass, and loosely speaking, this is about the content of metals you'd expect in gas giants in a solar system too. Whatever its star's metallicity was, as barring those very close to their sun, their gravity would have held on to all their mass, whereas hotter or smaller worlds, like our own rocky inner planets, would have originally had more hydrogen and helium when forming and lost them down the eons. If we think of that metallicity as our construction material, then our Sun has thousands of times Earth's mass in various construction materials, and is enough for creating an entire Dyson swarm of rotating habitats. Of course, as you extract mass from a star, you can either dump the hydrogen back down onto it to burn or use for other purposes. By removing the helium and other metals, you actually lengthen that star's lifetime almost indefinitely. Remove enough material and you dim that star too, meaning you need less material for a full Dyson englobement. You can also get metals the hard way via artificial fusion or using your power surplus to run massive supercolliders. Any way you put it, any star you find will always be convertible to a Dyson sphere of that kind you want with enough time and effort, even if you have to spend 1,000,000 years sucking metals and mass out of it while using your power surplus to run particle colliders to make heavy elements for construction. Fundamentally, this is why the Dyson dilemma of the Fermi paradox is always so compelling. The notion that there can't be a ton of alien civilizations around because if there were, they'd build such constructs not just around their own star, but everyone they colonized, and that the universe would be visually dark by now, with no stars in the night sky, because all that light would be absorbed by the Dyson swarms around them and re-emitted as infrared waste heat. See the Dyson Dilemma episode for more discussion of the notion. There are other pathways than building Dyson swarms for civilizations as they grow, assuming they do grow, but those pathways tend to resemble Dyson swarms, particularly in the astronomical sense of being visually absent. For instance, you could make artificial black holes for your power source, and dump hydrogen into them for power generation, see colonizing black holes, but you get a similar astronomical detection on that because a swarm can only be as dense as the waste heat it generates permits it to be. And you'd always want to build your swarm rather dense, since even a very dense one is still going to have large travel and communication lag time issues compared to folks living on a planet, even in super rural areas. That gives it the typical infrared waste heat blob appearance a Dyson would have, regardless of its power source, be it a star or artificial fusion, or a black hole, or energy beamed in from elsewhere, or whatever else we might use that does not violate the laws of thermodynamics. Should we do this? Should we dismantle our solar system? Well, it would seem the logical thing to do, but folks often object for many reasons. Some of these I don't find very reasonable, like notions that we'd have too many people. I understand the notion of having too many people for your available resources, but that's too many people to support, not objecting to the simple notion of higher quantity itself if you can support it. Nor is it just people. If you dismantle your solar system, you can use a tiny fraction of that mass to build wildlife-focused habitation cylinders and still have thousands of times the wildlife environments and ecosystems that a pristine Earth had. Of course, some folks object to the notion of dismantling those other pristine worlds, but I don't really think of big dead rocks in space as having much intrinsic value in just sitting there. A ton of random rock doesn't strike me as being as cool and neat as a ton of humans or a ton of kittens and puppies. Of course, as we saw, the sun has most of our building material anyway, so we could bypass those planets and leave them be, and we could also do that for Earth itself. The solar system has plenty of construction material, nor are we limited to just our solar system. Those great big solar collectors make a nifty way of moving materials between stars, as we looked at in our episodes Interstellar Laser Highways and Exodus Fleet. It is a bit of a pain trying to maintain stable orbits of billions or even trillions of space habitats, when you have great big gravity wells like planets orbiting around with them, but it is manageable, and if you are going to dismantle an entire solar system, well, most of that mass is hydrogen and helium, and they do actually have some construction value. You can use them for outer hull shielding against accidental collision or attack on a rotating habitat, or as a filler material on shell walls for making mass and gravity. If the latter, you can put planets in a ring around a star, what we call a Kepler or rosette, and that helps a lot with gravitational perturbation such planets cause a Dyson swarm, letting you keep Earth and have some additional classical spherical worlds, or even wheel-shaped ones like hoop worlds or flat disk worlds or sombrero planets. Needless to say, you can also fuse that hydrogen and helium into heavier elements, which if done right, produces energy rather than uses it. In that light, while it's a lot of work, many thousands of years worth at least, and not without some downsides, the upsides seem far greater. So for my part, I say it's a great idea. Let's dismantle our solar system. We were discussing a lot of astronomy and physics today, like calculating the gravitational binding energy of planets, moons, and stars. And if you're interested in learning more astronomical concepts, or the math and physics behind them, I'd recommend Brilliant. The universe is an immense and amazing place, and knowing the math and science behind it only makes it seem more amazing. And Brilliant's thought-provoking, fun, and interactive courses make them a great choice for learning, whether you're a student, a parent trying to enhance your kid's education, a professional brushing up on cutting-edge topics, or someone who just wants to use this time to understand the world better. You should check out Brilliant. Try adding some learning structure to your day by setting a goal to improve yourself, and then work at that goal just a little bit every day. Brilliant makes that possible with interactive explorations, and a mobile app that you can take with you wherever you are. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with your interactive explorations. Over time, you'll be amazed at what you can accomplish. If you'd like to learn more science, math, and computer science, and want to do it at your own pace, and from the comfort of your own home, go to brilliant.org/IsaacArthur and try it out for free. So next week we'll be back to the Fermi Paradox series to consider disappearing stars and cosmic voids, to consider such things are natural, or might be signs of an older alien civilization dismantling their own solar systems, or even entire galaxies. The week after that, we'll be taking a look at the popular science fiction trope of techno-barbarians, civilizations existing in a post-apocalyptic time using an anachronistic combination of primitive and advanced technology. But before that, we'll have our monthly livestream Q&A on Sunday, July 26, 4 p.m. Eastern US time. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website, isaacarthur.net, which are linked in the episode description below, along with all our various social media forums, where you can get updates and chat with others about the concepts in the episodes, and many other futuristic ideas. Until next time, thanks for watching, and have a great week.